In this video, I'm going to give a brief introduction to the idea of vectors. And so up here I have copied from Wikipedia all the axioms of vectors and their meanings here. I'm not going to go through all of these axioms. A lot of them will just be picked up sort of as we go along and sort of just use them. And there are very abstract and general definitions of what a vector is. I'm not going to go through that more abstract general. I'm going to keep it a little more concrete using this idea that most people are probably familiar with of an arrow pointing in a direction in space, so it has a magnitude and direction. And so that's sort of the more concrete, well, it's still somewhat abstract, but it's less abstract than what a vector actually is as sort of a type of algebraic structure. And if you're interested in that more abstract and general definition and things like that, I definitely recommend this channel and their playlist on tensors, which starts with very, very high level. I mean, I guess it's kind of complicated and conceptual, but I mean high level as in sort of looking at it from very high up and seeing it in very general abstract terms. And so it defines vectors and dual vectors and things like that. So if you are interested in that more somewhat more rigorous, somewhat more general and abstract, this channel is one that I highly recommend. Another channel that I recommend if you are interested in great visuals is 3 Blue 1 Brown. So they have a really great playlist on linear algebra that covers a lot of this kind of stuff too. I guess what you will get from mine is that I'm going to try and be very brief, and since I am actually not that much of a math person, I'm not terrible at it, right? I'm not great at it either. Perhaps my explanations will have that one thing in it that'll make something click for you, since the people who make these two channels, though these two channels are amazing and I highly recommend you watch and subscribe to them, these two people are really good at math, so they might have that issue where if somebody's really good at something, they don't understand how other people don't understand it, whereas I am not that great at math, so I know what it's like to not understand something and to have a difficult time understanding it. And so maybe having it explained by a dummy like me will help make it a little bit more clear. So I'm going to eschew all of this stuff up here and just start with, as I said, the somewhat more concrete idea here of a vector as being something that has a magnitude and a direction. So sort of an arrow in space is kind of the popular notion of it. And what we can do is, so in a lot of math, even higher level math, even things like general relativity, what you're essentially trying to do is get things to a place where you can use the Pythagorean theorem. So that's such an important theorem because it allows you to measure distances in space sort of at any angle. However, what you try to do is set it up so that you can get nice straight angles like this, so that you can use the Pythagorean theorem. So over here, this we have our x component. So I'm actually going to write that as a sub x component. So that's the how much this vector a sort of sticks over the x-axis here, and the a y component is sort of how much it sticks over the y-axis here. So you can imagine if you had maybe like a lamp right here that was shining light onto this, then the shadow that A casts on Y is its Y component. So this right here is the same length as this right here, and this is the same length as that right there. And so those are the same as the X components and Y components of our vector A. And you can do the same thing. Imagine a light up above here shining down, and the shadow on the x-axis is the x component. And so using that, we can then use our Pythagorean theorem, because if we want to know the length of vector A, that is the hypotenuse of a triangle, of a right triangle, where that's the right angle there. We have our theta right here, and so we can imagine, well, we don't have to imagine, we can know that the x component is adjacent to this theta, and so ax is equal to a, the vector here, multiplied by cosine of theta. And so we get the the x component here. Well, I guess this is finding the x component. If you want to find the length of A, you would actually use, so A squared equals ax squared plus a y squared. And so you can see, so we can see here that then what we end up with is if we want the length of it not squared, then we just take the square root of this plus a y squared. And so that's how we actually get the length of this. So over here, what I was doing is actually finding the component lengths. And so a y is going to be equal to our vector length multiplied by sine of theta, because now we're trying to look for this, which is opposite over hypotenuse, and that's sine. So these are how we find our components of this vector. And the angle here you can actually find, so if you know these component lengths, then you can actually find theta as the arc tangent, so arc tangent of ax over ay. Actually, I got that backwards, I believe. Yeah, it should be a y over a x. And so your y component and x divided by your x component as the argument for the arc tangent, and that will give you this angle here. Alright, and so if we move down here, we can talk a little bit about vector addition. So I have two different vectors here. If we want to add these vectors together, so if we want to add a plus b to get c, then we just take this and put it onto the end of a here. And so that would be something like this. So this is the same as b, and then we just go from here to the tip of that, and this will be our c, and that is just how you do vector addition. And to vector multiplication, I have over here, so if we have some constant, and so maybe we'd say this is double. So if we multiply 2 times a, then we can go from a here to, so c here, where c equals 2. So then it's just doubling the length of this right here. And then we end up with these different x and y components. So this was our x component here for the first one, and then this is the x component here for the c times a. And we can just use the same things I was talking about earlier to find the lengths of the components. So we could, if we wanted to find, so this is ax. So if we wanted to find ax after this expansion, that would just be, so c times a times cosine of theta, where that is theta right there. And so you're just doubling, or whatever you're multiplying it by, the length of this vector. And so you just take that into account here when you are you are scaled up. That's why it's called a scalar multiplication. So c is the scalar, and so you are scaling this up in order to you have to scale this up in order to find the new components, and you just do the same thing with y. Then the last thing I wanted to talk about was basis vectors. And so basis vectors are sort of your units. And so you can think about, the way I think about it is, if we have a number line and we have 0, and then there's some distance, I guess you could define, to 1, and then some distance that's the same as going from 0 to 1, that goes from 1 to 2, then the same distance brings you to 3. And so what a basis vector is that length right there. So the length, whatever length it is to get from one number to the next. So we define that as 1 on a number line, but you can define your basis vectors sort of arbitrarily here when you're using when we're doing vectors. But essentially, the thing you want, the things that'll make it easy for you is if they are unit, which means that you define it as 1. So kind of like up here, we could define a length here as 2. So we could define 0 to 2 as 1, but then you would have to call this length here 1/2. And so by making it unit, it just kind of makes your life easier. So we define one of these as 1. So this is defined as 1 in the z direction. This is defined as 1 in the x direction, and this is defined as 1 in the y direction. So those are unit vectors. And we also want them to be able to span. So span means that you can have a vector in any place in your vector field just using these basis vectors. So I have written over here one that does not span. So I have this triangle written here to show that these are all in a single plane, which means you could never have a vector that looks like that or that goes that way, because by combining these basis vectors, you can only ever remain in this plane. Whereas if you have something like this, then you can keep combining these vectors, sort of like what I have up here, in order to reach any part in your three-dimensional vector field. And so we want them to be able to span, which means that they are linearly independent. And so a good way to define what linearly independent is that if we take a times our ex here plus b times our ey here plus c times our ez here, and so these are just scaling each of these basis vectors by some amount. That's what this a, b, and c are. If these are linearly independent, then this equals 0, which means that a equals b equals c equals 0. The only way you could ever get a vector that sort of overlaps on each other is by multiplying all of these by 0, so that you just end up right here. All of your basis vectors are multiplied by 0, and so that makes it linearly independent. And so over here I have this image which is a 3D vector. So if we call this vector A, then we could say that this is our, well, over here we have a multiplied by e to the x. So e to the x is multiplied by some number to get this component of it. Then ey times, or ay times ey. So our basis vector ey has to be multiplied by some other component in order to get this component of our vector a. And then we have az times our basis vector ez here. So we have to multiply this basis vector here by some amount to get this length right here. And so that works sort of the same as in our number line. So if we say have this, so I'll rewrite it here. So 1 some length from 0 to 1, some length to 2, the same length to 3. And so we are defining our basis here as 1. Then if we want to get to 3, we have to multiply 3 times our basis. So 3 times 1 equals 3. That gets us to our basis. Whereas, say, if we defined our basis as being 3 long, then it would just be the basis times 1, and that would get us to 3 if we defined that as our basis, as sort of the basis of our number line. And so that's what we're doing over here. We've defined our bases as being unit, so equaling 1, and we have them spanning, so they're linearly independent. And we actually have these being orthogonal here. You could have something that's not orthogonal. So maybe if you had your x here, your y there, and then your z, instead of being straight up, is sort of off the perpendicular there. This could still be linearly independent in span. You could still combine these to reach anywhere in your vector field. But making them orthonormal like this, that's what it's called when it's like this, is orthonormal. Orthonormal. And that's another thing that will just help make our bases a lot easier to use, is making them orthonormal rather than having them be off like this. And so we've defined these as being 1, they're orthonormal, and we know that they are linearly independent and can span our vector space here. And so by multiplying our vectors, or our basis vectors, by some constant in each direction, then we can get the components for our vector up here. And so that is sort of the very basics of vector math here. As I said, if you're interested in these more abstract and general ideas of what vectors are, then I recommend particularly this top one, this guy XYLYXYLYX, in his videos on tensors. Actually, I think I have his. This is 3 blue, 1 brown here, so you can see their videos here, and this is the XYLYXYLYX. So you can see his playlists, his Lie groups and Lie algebras are really good. His mathematical foundations of quantum mechanics is still pretty preliminary. You can see it only has 4 videos. His largest one is What is General Relativity. I have only watched a few videos from that, but it's pretty good. The manifold one is really good, but the tensor one is the one that will cover what I'm talking about here. So we can open that up and you can see elementary vector spaces, how to make a map, dual spaces, that kind of stuff. So like I said, if you're interested in the more abstract general stuff, then that is the one I recommend. But I hope this was nice and short and easy to follow. And so I will see you in another video.